If we recall when we were looking at subspaces of Rn, what we had was, so here we were looking at, say, Rn. Inside of this, we had some vector space V, right? And then we were asking ourselves, or some subspace, maybe not necessarily a vector space, we were asking ourselves, how do you represent elements of V? For some subspace, right? Well, you need to you write them as a linear combination of what we now know are basis elements, right? You look at some collection of vectors, and that collection of vectors, their span uniquely determines every element in V, right? And this was the notion of a basis element, right? It gave you a basis for how to uniquely represent points inside of this space. This notion is the same, but we're going to define it a little more abstractly here. So let's let V now not be a subspace of Rn, but let's let this just be an arbitrary vector space. And then for some set of vectors V1 through Vn, let's let this be a subset of V, right? This collection is a basis for V if two things are satisfied. Remember that it spans V and that all the elements are linearly independent. So if we have both things hold, we have that V is equal to the span of V1 through Vn, and two, we have the collection V1 through Vn is linearly independent. Right, so this notion is the same, right? If you can find a linearly independent spanning set for your vector space, well, then you've also found a basis. Let's look at an example. Let's find a basis for P2. Okay, well, how do we write P2? Or what is P2 composed of? It's composed of elements AX, like AX squared plus BX plus C, such that A, B, and C are elements of the reals. Well, how would you find a linearly independent spanning set for this vector space? Well, this vector space in particular, we can find a spanning set based on based on what form these elements must take, right? These must take, for any P of X, this has to be equal to A times X squared plus B times X plus C times 1, right? And so we have that any element is already written as a linear combination of 1x and x squared. So we have that P2 is equal to the span of the elements 1x and x squared, right? Because really 1 on its own, this is an element of P2 with A equal to B equal to 0 and C equal to 1. We have that X is an element of P2 with A equal to C equal to 0 and then B equal to 1, right? And then same for X squared with A being 1, B and C being 0. Could we prove that this is linearly independent? Well, sure. How do you have AX squared plus BX plus C equal to 0 without A, B, and C all being 0, right? Well, you can stare at that for a while and you can't, right? The only way this is equal to 0, this is if Because remember, this polynomial has to hold. This must hold for all x, right? You may say, well, let me just take x equals to 0, and then a can be non-zero, b can be non-zero, and then c was b0, right? That is only true for a specific x value. This has to be true for all values x, right? The only way this polynomial is equal to 0 for every x value is if a is equal to b is equal to c is equal to 0. So we have a basis for P2 given by 1x squared. So this means we could find a basis for Pn for finite, like fixed finite n, right? The basis for Pn would be given by 1x squared, blah, 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 all the way up to xn. And let's remember a definition really quickly. We have the definition that the number of basis elements this is equal to the dimension of the vector space, right? So let's let V be a vector space here in this definition. Then the number of basis elements for some basis of V, this is equal to the dimension of V. And so what does this mean? Then the dimension of P2 is, right? The dimension of P2 is equal to 3 since the basis is given by 1x squared. And so you can see that the dimension, when you generalize, the dimension of P sub n is equal to n plus 1. Now, if you'll remember, I talked about the space P infinity, which we don't really write as P infinity. We write this as R adjoin X, right? Which this is the collection of polynomials in X, right? So this is like a0 plus a1x plus a2x squared plus et cetera, such that, or better yet, let's write these as series, right? Sum I goes from 0 to infinity, ai x to the I, such that the ai's are in the reals for all I, right? Then you could ask yourself, what's a basis for this, right? Well, a basis for P sub infinity, this is going to be 1x squared, x cubed, et cetera. It's going to be an infinite set, which implies that R sub x is an infinite dimensional vector space. Right, which is kind of cool to think about, infinite dimensional spaces, as much as we can think about it, right? We're restricted. We can't even think about 4-dimensional vector spaces all that well, let alone infinite dimensional vector spaces. Okay, let's see a theorem here that relates subspaces and dimension of vector spaces. So theorem, we have that W contained in V, let's let this be a subspace of vector space capital V, then we necessarily have that the dimension of W is less than or equal to the dimension of V, right? So that's saying number of basis elements for a subset cannot exceed the number of basis elements for the overall set itself. And we have another statement that the dimension of W is equal to the dimension of V if and only if W is actually just V, right? Or if W is isomorphic to V. So we have this restriction on dimension with equality holding if and only if the subspace is the overall space. And that's fine because we think about a subspace as being a subspace, or a space as being a subspace of itself. Let's look at another example here. Let's look. Let's say U is given by the set of 2x2 matrices A. So A is an element of M22 such that A times the matrix 1, 0, 1, -1 is equal to 1, 1, 0, -1 times A, right? So remember M sub 2 is the set of all 2x2 matrices. This subset U here is the set of all 2x2 matrices that satisfy this condition. Now let's find a basis and the dimension of U. So how do we do this, right? Well, we find a basis by, we always look at what our restrictions are here. Let's write A. A is a 2x2 matrix. So let's write this as A, B, C, D. Let's write this entry-wise. And now we need to understand what these restrictions, like this restriction up here, that this product is satisfied. We need to understand what this restriction means entry-wise for these 2x2 matrices, right? So we need to look at A, which is A, B, C, D, times 1, 0, 1, -1. And let's see what that gives us. Well, and then why don't we just do this both sides at the same time. So we need this to be equal to 1, 1, 0, -1 times A, B, C, D, which we do the product on the left. We're going to get A plus B for the 1, 1 spot, and then -B for the 1, 2 spot. We're going to get C plus D for the 2, 1 spot, and then -D for the 2, 2 spot. We'll do the same thing for the multiplication on the right. For the 1, 1 spot, we're going to get A plus C. For the 1, 2 spot, we're going to get B plus D. For the 2, 1 spot, we're going to get -C. For the 2, 2 spot, we're going to get -D. And what do we learn from this, right? Well, two matrices are equivalent if and only if all of their components or all of the entries are equivalent. So the first one tells us that A plus B equals A plus C. The second one tells us that -B equals B plus D. The third one tells us that C plus D equals -C, if I'm not mistaken. Yes, and then the last one tells us that -D equals -D. What does all of this tell us? Well, this tells us that B equals C. This tells us that 2B equals -D, tells us that 2C equals -D, and then it tells us that D equals D. You'll notice we have two free variables here, right? We have D equals D, that gives us a free variable, and then the A's vanish everywhere, right? So A can be whatever it wants, and we have no restriction. So let's introduce some parameters here. Let's say A equals S and D equals T for S and T in the reals. Then we have what? We have that A should be S, B should be equal to -1/2 T. We have that C should also be equal to -1/2 T. And then we have that D is equal to T. We've now described what elements of U look like, right? So elements of U necessarily look like, plugging everything in, this implies A, these matrices are of the form S, -1/2 T, -1/2 T, and T for S and T and R. Great. So now how do we find a basis though, right? We have these, we have now a much more explicit description of what elements of U look like, but how do we find a basis for these, right? What we need to do then is we need to be able to write all of these matrices as a linear combination of elements of M22, right? So we notice if we pull out an S, this is equal to S times, and then what? We would have a 1 here. And then if we pull out an S, well, for this to be true, we would need zeros everywhere else, right? So here, actually, let me write this a little differently. I'm going to split this matrix up into where I'm handling entries with S in one matrix and then entries with T in another, right? So let's write this as S0, 0, 0 plus 0, -1/2 T, -1/2 T, and T. I like that approach much better. And now we can think about pulling out an S or pulling out a T, right? So if we pull out an S from the first matrix, we have S times 1, 0, 0, 0. And then if we pull out a T from the second matrix, we have 0, -1/2, -1/2, 1. And now we have described all elements of U as a linear combination of the matrix 1, 0, 0, 0 and 0, -1/2, -1/2, 1. So this implies that a basis for U is the set 1, 0, 0, 0 for the first matrix, and then for the second matrix is 0, -1/2, -1/2, 1. This also tells us that the dimension of U is equal to 2. So this is a two-dimensional subspace of M22, okay? And so I didn't prove that this is a subspace here or that this set spans. Well, we've just shown that it's a spanning set, right? It's clear to check. You can see very quickly that these two elements are linearly independent. That's something I would have to do that I have not done, right? But I challenge you to show this. You can almost show this in one line. It's a very quick check. But I also didn't say that this was a subspace. I was you can show that this is a subspace, but I was under the assumption that we were using this as a subspace, and it is indeed a subspace. I just wanted to make sure I vocalized that I was taking that for granted, right? In general, you could not skip to this step until you had already shown that U is a subspace. Okay, cool. Now, let's talk about extending a basis. So let's do another example here. I guess our example is blue, where we extend a basis. Extending a basis. So let's say we have the set S, which is composed of, it's a subset of M22. So we're looking at 1, 0, 0, 0 and 0, 1, 0, 0. It's very clear that this is a linearly independent set and that this is also contained in, this is also contained in M22. Now, what we want to do is extend S to a basis of M22, okay? And how do we do this? Remember, we had this following theorem a while back. We proved it a few videos ago, I think. And what you have to do is you have this collection of vectors. Remember, let's say like V1 through VK. This is a linearly independent set. And then if you have that V is not in the span of these, V1 through VK, then if you add V to this collection, then this is also linearly independent, right? So what we're doing here, we're using this theorem. This is some theorem that we stated and proved. Maybe not the last video, but maybe a couple videos ago, right? Remember, if you have this collection of linearly independent vectors and you have some other vector that's not in the span of those linearly independent vectors, well, when you add that to the collection, then you've increased the span or you've increased the number of linearly independent vectors that you have in this collection. So when you see the problem come up that says extend some set to a basis of M22, what are you trying to do? You're trying to find linearly independent vectors that do not belong to the span, right? So what do we need to do? This means we need to find A such that A is linearly independent to 1, 0, 0, 1 and 0, 1, 0, 0, but A is not in the span of S, right? We were calling those two S. Well, what is the span of S? Right? The span of S is the set of all matrices, let's say capital M, such that A times 1, 0, 0, 0 plus B times 0, 1, 0, 0, right? This is the span of S. It's a collection of these matrices, i.e. it's matrices that look like A, B, 0, 0. What then, right? We need to find a matrix that is linearly independent or that cannot be written as A, B, 0, 0. And you might see right away, well, find any matrix with a non-zero entry in this spot, and that can't be written as something in the span of S, right? So let's take R, or let's take some matrix A to be 0, 0, 1, 0. Well, certainly that's not in the span of S, because elements in the span of S necessarily have 0 values in the bottom two entries, right? And so that means we could, and you can very easily verify that this is linearly independent, and then you take R to be the set of, it's going to be S, right? So these first two elements here constitute S, and now we've added one element here. Cool, so we've extended this spanning set to include a larger subspace of M22, but is it all of it? Well, you may notice now, what's the span of R? The span of R is going to be those matrices M such that, you know, A times 1, 0, 0, 0 plus B times 0, 1, 0, 0 plus C times 0, 0, 1, 0. This is equal to all matrices of the form A, B, C, 0. Can I find a matrix that doesn't belong to this span? Sure, I just have to find a matrix such that the 2, 2 entry is non-zero. So let's take B equal to 1, 0, 0, 1, right? And then let's add that. You can again verify that this is linearly independent from all of these in R. And then we'll call T this following collection. So it's S, the elements of S, right? And then the added element that made it R. And now we're adding a final element, and we're looking at the set T here. Now, what is the span of T? The span of T is going to be M such that, you know, A times 1, 0, 0, 0 plus B times 0, 1, 0, 0 plus C times 0, 0, 1, 0 plus D times 0, 0, 0, 1. This is equal to all matrices of the form A, B, C, D. Well, we know that's actually just M2, 2. And along the way, we were verifying at each step that this collection here is linearly independent. And so now that means T is equal to a basis for M2, 2, right? So here, and this is actually a very standard basis for a matrix space, right? It's just you have to have 1 in every entry and then a 0 everywhere else. And this also shows us that the dimension of M22 is equal to 4. You can generalize the dimension of MN, as you can imagine, is the product in times n. Alrighty, I think that's everything I want to talk about for and examples to explore of looking at subspaces and bases for arbitrary vector spaces, right? We've seen some examples now for polynomial vector spaces and matrix vector spaces. Next, what I want to do today is quickly look at sums and intersections of vector spaces. This will be a notion that we did not explore when we were looking at all these concepts in Rn, but we will now explore in the general context of vector spaces.